Dear students, today we will talk about exponential and logarithmic equations. Exponential equations are those including two expressions, at least one of which has an unknown variable in the exponent. These expressions can have equal bases, different bases, or one of them can be just a constant. For the sake of clarity, a simple exponential equation can be solved using plots. The left-hand side in this example equation is an exponential function, and the right-hand side is a linear polynomial. Both of them can be treated as separate expressions, and the graph on the slide shows their plots. Like you see it here, the first one on the left and the second. The point where two lines intersect here belongs to both of them, and consequently its horizontal coordinate is the value that makes the equality true. Here. From the plot, one can see that the intersection point has 1 and 2 forward coordinates, and x equal to 1 is the solution to the equation in question. This solution has to be unique, since the linear function is decreasing and the exponential one is increasing monotonically. Therefore, their plots cannot intersect anywhere else. But in practice, using graphs for the solving equation is inconvenient, since plotting the functions manually can be time-consuming. Moreover, the exact coordinates of the intersection point can be found almost only when they are integer. That is why other methods are used for analytical solution, for example, equating the exponents. The properties of exponential functions show that two powers with the same base are equal only when their exponents are equal to. This means that after transforming an equation so that its sides contain an exponential expression with the same base each, one can then go from an exponential equation to a polynomial one by equating the exponents. Consider the following equation as an example. 81 is the fourth power of 3. We are here. This one leads to this. So the equation can be transformed in such a way that both sides include powers that equal base of 3. Then the exponents can be equated, thus forming a new, simpler linear equation. This one is solved to find the unique root. A more complicated case requires introducing a new variable. Usually this turns an exponential equation into a quadratic one, which is much more simpler to solve. After that, the roots are substituted into the initial equation and the overall solution is found. When performing the substitution, it is necessary to remember that an exponential function yields only positive values, so negative and zero roots must be excluded from the solution. Consider the following example. The initial equation is transformed to the first term is a square of 3x. By introducing the new variable, we have it here, and our new variable will be t. Equation is turned into a regular quadratic equation, which is then solved yielding to two roots. The first root is substituted into the initial equation, and x equal to 2 is found. The second root of the quadratic equation is negative, and substitution forms an equation that has no roots. Those equations where the unknown variable is under the logarithm sign are called logarithmic, as the name suggests. The possible methods of solving them include using the definition of the logarithm, introducing a new variable and raising to power both sides of the equation, and applying a logarithm to them. Simple logarithmic equations can be solved straight by using the definition of logarithm. Such expressions contain a logarithm on one side and a constant on the other side of equal sign. Solution is quite straightforward, as shows the example on this slide. First, one has to check for the range in which the unknown variable may change. The argument of a logarithm must be positive, and if there is more than one logarithm in this equation, then the strictest condition should be selected for the variable, so that all of the arguments are positive. Here, in our case, the argument of logarithm is positive for any real number because of the square and the positive term added to it. Then the second step is raising 4 to the third power in accordance with the logarithm definition. This gives us a quadratic equation with 2 roots. Both of them here are acceptable for a solution because previously we have defined that the range, they are known to be from -infinity to +infinity. Introducing a new variable is done nearly in the same way as we talked previously with the exponential equations. Another method of solution is going from a logarithmic equation to an equation that consists of their arguments. Of course, the bases of the logarithms must be equal. It is implied, in fact, that both sides of equations serve as an exponents for the same base. Before transformations, once again, we should check the allowed range of values for the unknown variable. For example, here in our example 4 is in an allowed range, so it is accepted as a solution for the initial equation. The opposite of the previous method is applying logarithms to both sides of an equation. If the base of the logarithms is the same, then the resulting equation is equivalent to the initial one. Applying logarithms is implied when solving purely exponential equations like those we have seen in the beginning of the lesson. Anyway, sometimes a logarithm is placed in an exponent and the other side of the equation is constant. This is where applying logarithms to both parts of the equation is useful. In this example here on our slide, first the range is checked in which the unknown variable may change. This time it includes all the positive numbers except unity. After applying logarithms to both parts of an equation and using one of their properties we have mentioned earlier, we come to a quadratic equation and introduce a new variable to solve it in an easier way. Substituting the obtained solutions into the initial equation, we get 2 roots for it. Both of them suit the possible range of unknown variable and are included in solution. Next time we will talk about trigonometric functions, their definitions and properties.